All right, welcome to the Module 5, Chapter 9 lecture. Much like the Chapter 8 lecture was very long, this one's going to be much shorter. The material is beyond what's necessary for construction managers. Um, it's some background that's significant, I guess, for GPS, but in reality and the way things are utilized nowadays, you're not going to need very much of this information other than to understand how things work and what happens. So here we go. I'll start the slideshow. And again, this will not be a very long lecture. And we'll get to this screen here. We're sharing our screen. All right, very good. All right, so Chapter 9, satellite positioning. Uh, Most of you understand this as GPS, Global Positioning System. We all have GPS on our smartphones nowadays. GPS is built into your cars, and airplanes all have it, boats have it. Anything that needs navigation will have GPS anymore these days. But from a construction side, we're going to start to introduce you to satellite positioning. And what that gets you to is being able to utilize survey control that's done with satellite receivers. It's also going to get you to have machine control. Later in the book and later in the semester, we will talk about machine control and its benefits for construction industry. Um, so, Chapter 9. So in 2021, I've updated this slide from what was in your textbook. We have a bunch of different satellite systems nowadays, and satellites literally these are a satellite is something that orbits the Earth. It could be a rock. It could be considered a satellite. The moon is considered a satellite of the Earth. But these are communication satellites. I forget the distance they are above the Earth, but it's just above, like where commercial planes are at 30 some thousand. It's something just above that, outside the reach of aircraft. Uh, but they're pretty high, but they're right there so that they actually appear to have a fixed position. They're put in such an orbit that they are not drawn any closer to the Earth, and they are not released out into the atmosphere. That way, they appear to be fixed. They don't move in relation. If there's a place on Earth, say the Washington, D.C., and there happens to be a satellite over top of it, it will always appear to be over top of Washington, D.C. So with these things being fixed in the sky, we tend to have positions that we can work from. But there are 4 major constellations of satellites. Navstar, which is United States, it's referred to as GPS, actually, is what most of us call it. We now have 31 satellites available, and I think maybe 32 is going up very shortly. So these would orbit the Earth, and we can utilize them for positioning and navigation, as well as many other things the information these satellites carry and transmit. But for our purposes, we're looking at least 31 in the United States. Now they orbit the Earth. So Russia has 24 satellites. Theirs is called GLONASS. They have 24 satellites. Much of them are available. It says here from the book, most satellites of any full constellation. In other words, you can see many of them, more of them at once, but I'm not sure quite how that statement is probably not true anymore with what China has done in the United States. The book doesn't even acknowledge that this was online anymore. These were brand new in concept. So Galileo is a European constellation with 24 satellites. And then this Beidou is China, and it has 35. China has the biggest satellite system for navigation. They are completely autonomous as well. The government in China has enough information on these 35 satellites to not share or not need the use of anyone else's satellites. So why is that important? Well, I guess it's important for China, but for us, what we use in the surveying world is I use all three of these right here. All three of those systems are available for me to receive a signal from when I'm measuring and doing survey work. So with that being said, I mean, I have a choice of what, 31, 24, that's 55, 75, 79, 79 satellites are available to me to get a signal from and pinpoint my location. My GPS receiver routinely will receive 18 to 20 satellites at any given time as far as a clear signal, clear enough to be able to measure from. So it's interesting that we have all these things available to us, and our technology allows us, at least from a survey wise and a machine control, that we can utilize all three of these networks. Nobody's utilizing China very much. I think China has a recent contract with Taiwan, government of Taiwan, uh, to do for them to use their satellite system, but other companies and other people are not using the Chinese network. So there's an overview of what we have going on. This type of situation here, you see all these different orbits. Um, I don't believe the satellites really quite orbit this way around the Earth. It seems to be that most of them are in this range right here of angles. We'll say that this one right in here, let's say that is at the equator. Most of the satellites are on the equator or slightly above and slightly below. I don't believe we have too many GPS satellites that orbit the Earth in a north-south pole type situation. I could be wrong, but I don't believe so. I think that the radio signals are enough that when the Earth is tilted, they're receiving enough information from each of the satellites. So the next slide, we will see that satellite signals, this is not that important to you. I'll explain what you need to know from it. In fact, these are actually old right now. The current signals that everybody is using are L1C, L2C, and L5. The C's are a different version. They got away from the CA code, and these P codes are not the same anymore. The satellites may still broadcast these frequencies, but it's only for older equipment, and at some point this may be turned off if it's not already. So the L1C, L2C is what is used for private navigation. I say private meaning what we get to use, surveying and construction, as well as your cars and your boats and anything along those lines. The L5 signal, which I don't even think, yeah, they're not even mentioning L5 in your book. L5 is primarily used right now by um, aircraft, military, and perhaps some other safety features, some other safety type associations, I'll call them. But yeah, I don't know if the ambulance and fire departments, rescue squads and fire departments, I don't know if they utilize L5 or not, but L5 is definitely the military, people like Coast Guard, that's military as well, but those type things, as well as our private and commercial aircraft, will use L5. L5, they did that so that it's for safety purposes, public safety, and it's a very robust signal with a very wide bandwidth, and a lot of people can use it very quickly, and it stays free of clutter and chatter from the populace. So we have three now, and the way these work, they have a frequency which is not important to us, but just think they're on a wavelength. These radio signals are transmitted from a satellite at a wavelength. The wavelength literally, is a sine wave. and it goes up like that and back down. The number of wavelengths from the, I should go back, the amount of time it takes from the signal to be transmitted and received is then computed. A distance gets computed because we know how long it takes to receive a signal. And if it takes, however many seconds long to receive a signal, then you realize you can, you've received so many wavelengths, and that gives you a distance. That's the simple part of it. Again, a slide like this is not that important with the different codes and how they all work. Just realize things are transmitted from satellites, and we're dealing with a difference in time. We are measuring in time, and the amount of time something takes can translate into the distance, because we know how long it takes for one single wavelength to complete its, for the radio wave to complete one wavelength. We know the amount of time that is, and then you just multiply that by the total time and you get your total distance. Here's what you're looking at. A receiver will receive multiple signals at the same time. We have X, Y, Z values, which are, again, they're stationary over top the world. And these Z's are a height. So this is an X and a Y coordinate, which we learned last chapter. There's northings and eastings, or latitudes and longitudes. And Z is always the elevation that you're at. These are the distances that come in, as well as you can begin to figure out the angle, because we know where each one of these is. And based upon these two distances here and a known arc distance out here, we can figure out this angle. You take this angle and you can start comparing it to all the other angles. And we're getting to see what we will actually start doing right now. We create this baseline here on Earth by getting multiple satellites, but we're looking at a distance and a distance. Once you have more than one satellite up here, you can't actually get this from one satellite. You have to have at least 3 satellites to get a position on Earth. But once you have this other one, you start to get an angle here, and then you can work out your angles here. And you're basically using a trigonometry that we have discussed in the first part of the lesson, or first part of the semester. So you're working triangles. Sometimes you have an arc, like up here, we have an arc, but we still know the distance in the arc. And so you can always figure out what's going on down here on the ground. Again, here's what I was getting at. You have to have more than one satellite to be able to get this position. And the goal is to receive multiple positions here, and you average them out. The software that I have uses a least squares adjustment, a statistical analysis that we touch bases on for chapter 8 with regards to traverse closure. So it does a statistical analysis to eliminate all the errors and figure out what we have here. And the same thing happens here. And then you can get a baseline, a distance, and a bearing between these 2 points by all this averaging that goes on out here. Again, now you're just starting to see a bigger picture. You don't have to worry much about the technical names like this with regards to triple difference. It's just not important for what you're going to be doing, nor is it very important for what I do. The satellite software we have that handles all of this. And like I said, at any given time, I can be sitting here on the ground and receive signals from 18 to 20 satellites every second. And the software is computing a new position every second by basing all these different measurements and they're averaged together and come up with an answer every second. And so you're not just looking, when you see something like this, you're not just looking at um, like one angle, say right here. You're going to compare this angle with this angle right here, and with this angle right here, and with this angle right here, and this one, and this one. So when you have 4 satellites and you're getting a measurement down here, you have 4 separate distances, but you also have 1, 2, 3, 4, 5, 6 angles from the 4 satellites that you actually are also measuring, and you're getting an average, and you're weighing all that information to get you down here on the ground with one value. And that's generally how it works. This technique is done now. I used to have multiple receivers. I would have 3 or 4 receivers, and we did something called static observations. Now we use real-time kinematic surveying, and those terms are going to pop up here later. Right now, most people just have a single receiver, and the other receiver is a base station that you access over the internet, so that you're coming up with 2 receivers. Um, double differencing, why does it says 2 simultaneously? Oh, it's where it's receiving signals from more than one. These are very similar. It's just a matter of how you receive your signals. But in our case, today's technology, most of us are going to use some real-time network, and we're going to have one receiver in our possession, or one receiver mounted on top of the bulldozer, or any other piece of equipment, and then we're going to be tied to the internet for the other receiver. There are ways, we have base stations, and we can talk about that more as the semester moves on. The triple differencing here is again, it's not that big a deal, but it's just more receivers and more satellites and more information that you're receiving. We do want to talk about errors. So with errors, there's many different errors that come into play with a satellite signal. One is the clock error. We used to have to synchronize watches and make sure that we had accurate time taken when we collected data with a GPS. That's all gone now. It's because we're tied into the GPS, we're tied into the internet. We have good clocks. The atmosphere, the ionosphere, that definitely has a factor, but that can take into account. I'm going to skip this one right now and skip this one. Um, errors in satellite orbit data. Every now and then a satellite will get out of whack, and there could be errors in that. And then, of course, you need to set up your equipment correctly. I've seen people not set their equipment up, and right off the bat, they're putting error into a setup that might not be too correctable right here. This information here is also something that you have to watch when you're utilizing the GPS. A weak geometric constellation means, I'm in some tree cover and behind a building. I can only see 4 or 5 satellites. That's going to give me the quality of my answer is going to be less than if I was receiving 15 or 20 satellites. So you have to watch for this right here. You have to watch for how clear your signal is getting to you. Sometimes it's above and below the horizon and things aren't very good. But this is something that every receiver will tell you is going on, and has the different ways of measuring it. But the general one is called a PDOP. That's what most people see and recognize as strong or weak geometric configuration of the satellites. This one here, multipath, is something that you also have to watch for. So the satellite signals are coming down constantly. They're hitting the ground. There's nothing you can do about it. So when you set up a receiver to receive those signals, it's going to pick up the signals as they come straight down from the sky. However, if you park your truck next to it, let's say 5 or 6 feet away, the satellite signals will also come down and hit your truck, and they'll bounce off your truck and be received by the satellite receiver, such that the amount of time now for that particular signal is different. And this is called multipath. You can avoid multipath errors by keeping things away from your receiver and just letting it hit the ground. The ground tends to absorb the signal more than anything else. But you're still going to have some multipath issues going on. And the way you achieve this is by longer observations. The longer the observation, the software better filters out the multipath signals that are, you're collecting, we'll call them like secondhand, after they bounce off of something and come back to the receiver. So the multipath, the weak geometry, and the setup errors are all things that you can handle and work on as an operator of GPS equipment. GPS measurements. We basically have a few types of measurements. I mentioned earlier static, kinematic, real-time kinematic. We're not going to worry too much about this one. A core station is a continuously operating reference station. You don't need to worry too much about that either. This information is built into these networks right here. So the main things that people use today are static and real-time kinematic, as far as you actually using something in the construction industry. A static observation is when you want good survey control. Like the couple points you need to start a boundary traverse or a control network, control traverse. Static observations, you sit on a point and you receive a signal for anywhere from 25 to 40 or 50 minutes, maybe even an hour. You receive a signal for that long, and you will compare it to information that you were doing on another setup. So you're always comparing it to somewhere else. So you always have to have 2 points on the ground. So the other observation could be, you can go on to the NGS, National Geodetic Survey site, and you can get other static information from satellites, base stations that are around your area. You can have your own base station that we mentioned earlier, where you actually have 2 satellite receivers at the same time. And I told you I used to run 4 at the same time to collect data. And that way you can get multiple answers at the same time on different points and just speed up your process. The other method for static observation is utilizing the reference stations that are in your real-time kinematic network, or an RTN is what's not shown here. Kinematic surveying, we don't really do it anymore. It was some early kinematic surveying when we had static receivers primarily. Now this real-time kinematic is we're connected to the internet, and this is what you see in the videos I showed you. This is real-time kinematic. You connect to the internet with your roving pole, your one single receiver. So while you're receiving signals, satellite signals, you also have an internet link, which is connecting you to base stations in your network, that now you have 2 points on the ground and you're now able to figure out your position. Cores are things that continuously operating reference stations. This is a GPS receiver that is sitting in a fixed location and never moves and continuously operates and transmits its results very quickly. Like every second or every 5 seconds, you're getting a result from these being transmitted. And that's what real-time networks, back up here again, that's what real-time networks use these core stations and their data to establish a network that you can tie into when you dial up on the internet. And that's how we use the GPS for measurements today. These types of things, they're obsolete anymore unless you're doing a controlled network. You don't need to be bothered with collecting all of this data. We're going to use real-time networks to give us the information we need in most cases, including your machine control. Something like this is not too important. You can look at it if you want. It's really, you're not going to be utilizing too much of this information. Most of the time we're going to collect data. We may do a little bit of, we're going to do, these are like in a data collector. We're going to be collecting survey data. We're going to be staking information out for construction stakeout purposes. And we may end up doing what's called an inverse, where we check distances between points. And here's COGO, where we might compute some things. Otherwise, we're not going to be doing too much of this inside a data collector for construction stakeout purposes. And machine control is even less of this information. I do want to point out here, and this is the last slide, you point out there's different areas that we actually are working with. And the book explains this fairly well. We have the actual surface of the Earth. It's up here, and that's really what the Earth looks like. But we have to have models. We have a geoid model, which is a mimic of the surface. And then we have ellipsoid models, which tend to be a singular rounded shape. Not a perfect circle, but a singular smooth shape to mimic the size of the Earth and the shape of the Earth. That's the ellipsoid. GPS takes into account both of these right here. And we're constantly having to figure out the heights between each of these levels to be able to give us an accurate information, accurate location right here where we're surveying on the ground. So if you have any questions, I'm not going to ask you much about this right here. You can shoot me an email or send me a text or something if you have questions. It's not that important for what we're going to do, because again, our software will take into account these types of things. You just have to make sure you have the right data put in your software, and then you can use your data collector and get the correct information you want. So let's stop sharing. And pretty much that is the end of chapter 9. It introduces us to something that is pretty broad and pretty cool when I think about where we're coming along in the chapter, or in the book, I mean in the semester. We start off with chaining, and you're pulling a chain on the ground, and you're measuring the ground like you would a piece of lumber before you cut it to build a deck or a picnic table or something. So you're measuring the ground with a chain. We're measuring with a stadia rod, the printed rod that you had to read last week all the time. So we're doing those things, but then now we're moving to satellite positions. And I wish I had the ability to meet with you in person, because I would give you my satellite receiver and you could walk around and see how quickly you can locate and map something like a parking lot. It's very easy to use. Once you get it set up and you know what you're doing and you have all your safeguards in place, it's very easy to use it, and it collects data very quickly. So please watch the videos I provided you on traversing, and please watch the videos on the GPS receivers. They will help you, and they'll do a pretty good job, since we can't meet in person and we don't have our hands on the equipment. So this week's assignment is not too much, not too terrible. Again, we're going to be wrapping things up and moving forward, and I look forward to seeing everybody next week. Thank you.